Okay, so for our last subtopic of our physical properties, we're going to talk about mass, weight, and density. Now, if you all look at this, how come mass and weight is different? Because mass and weight are actually two different things, but in layman, when we are talking about in day-to-day life, sometimes we mix them up usually. So now we're going to learn about the difference between mass and weight. Okay, now firstly, what is mass? Now typically mass is symbolized with a small letter m. So you have a number and then you have a unit over here. Take note that this is your SI units. Okay, so kilogram, it is the amount matter, the amount of substance inside a body, as long as you remember mass is this. Okay, so every object that you can see, smell, touch, and everything like that, those are all made of atoms and molecules, or you can just call them particles. Okay, so if you're not too sure which one is which, just say the word particles. As long as the number of particles do not change, it will remain constant. Why? Because it's the amount of matter inside your body. Again, then we have this thing called inertia itself. Inertia is a little bit special. Inertia is rarely tested. Inertia is the tendency to remain in motion if you are already moving, or you are at rest to remain at rest. Okay, so basically it is the tendency to resist changes to its motion. Okay, changes to its motion. So if you are already moving, you want to remain moving. If you are already stationary or at rest, you want to remain at rest. So inertia is trying to keep you from changing. You don't like change. So the only way you can change is when you have an unbalanced force. Okay, so don't worry about this. This one is when you learn the forces chapter, it'll make more sense to you at that point in time. So just need to note your inertia is proportional to your mass. Now, this proportional, what does it mean? It means as mass increases, your inertia also increases. So the opposite is the same as well. As your mass decreases, your inertia, there's no symbol for inertia, also decreases. So they are linked side by side. Okay. So the thing is, when we measure your mass, we will use a beam balance, but this is only for comparison. For comparison only, this is what we use in school lab. Okay. So if we are doing an actual experiment itself, we should be using an electronic balance. But if we are comparing it in terms of words, compared against weight, we'll be using the beam balance. So for those who don't know what a beam balance looks like, it's basically something like this. It's like the scales that you have that is balanced. This is what a beam balance. Okay. Now next, weight. Now this is very different from your mass radii. Weight is also what we call gravitational force. So the thing is, weight is a force. It's no longer a mass. So because of this, this is different. So W is actually in terms of newtons. Look at the units. It's no longer in kg. Okay, so it's totally different from your mass. They are not the same. So you need to take note weight. Now, everything in kg in normal day-to-day life, right? But now, starting from now, from secondary school onwards, we do not use weight for kg. Weight is newtons. Mass is the one that is in kg. So next time, if you go and check your height and weight, basically you go and ask them, hey, what's your mass? Not your weight. It's actually height and mass, not height and weight. Okay? But basically, this is for school. If you are day-to-day life, if you say weight, it's gonna confuse you. So try to say mass if you're counting in kg. If you're counting in newtons, then it'll be weight. Okay? It'll be slightly different. So on the next page, let's take a look. So the formula is this. W is equals to mass times gravitational field strength. Now, this G over here is gravitational field strength. Okay, it is not gravitational force. It is your gravitational field strength. Slightly different. Okay, so the thing is that basically it is this formula, W equals mg. I'm not going to delve too much into this. You just need to know that weight is mass times something else. That's why weight and mass, they are not the same, because you only get weight when you take mass times gravitational field strength. Okay, and I think there's a typo here, is gravitational field strength. Okay, and for your weight, we'll be using a spring balance. Now, actually, all these force meter and Newton meter, they are actually all your Newton spring balances. They're all the same. Basically, it is this device. 1, 2, 3, 1, 2, 3, 3. You have a hook here, there's a spring inside, and then there's a hook at the bottom. So inside here, there's a spring. That's why we call it a spring balance. So typically, you will just place your object over here. You have a pull over here, and therefore you can read readings. So these are your readings. Okay, so basically your beam balance uses mass on one side to measure mass on the other side. Your spring balance uses your spring force to measure the weight, which is a gravitational force. So a force to measure a force. So mass to measure mass. So they are different in this way. Okay, so let's try to solve the weight question. So a simple weight question. So first things first, they tell you that G on Earth is 10 newtons per kg. G on the moon is 1.7 newtons per kg. The object is 5 kg on Earth. What is the weight of the object on Earth? First thing, W equals to M times G, right? And because they tell you on Earth, all the values you use must be Earth, Earth, Earth. So weight on Earth, mass on Earth, G on Earth. What's your MS on Earth? Is 5. What's your G on Earth? Is 10. So you will get 50 newtons. Okay. So how do we get 50 newtons over here? Sometimes if you actually look at the units, it's 5 kg and 10 newtons per kg, right? So the kg and kg will cancel out. You actually end up with just 50 newtons. Okay. Next, what's your mass of your object on the moon? Now, mass, if you remember back, is the amount of matter in the body. So ask yourself, when I bring my object to the moon, did my mass change? Did the amount of substance, the amount of particles inside it change? It did not change. So your mass is actually the same on Earth as well. It's also 5 kg. It didn't change. Same amount of substance. Okay. Now, last but not least, what's the weight on the moon? W on the moon, mass on the moon, G on the moon. So 5 kg as well. Your moon is 1.7. So you press your calculator. You end up with 8.5 newtons. So you can see it is lighter on moon. So it's easier to carry stuff because the gravitational force is weaker. Okay. So you can see over here, everyday time, we just say mass and weight, we always say the same thing, right? But in science, they are different. Not the same. Okay, so let's look at the comparison. First one is actually your definitions. Okay, you can ignore the second one. You haven't learned that. This is your SI units, your instruments, and then this one is regardless of location. Okay, otherwise some students will get confused. Oh, mass must be constant. No, mass is constant unless you chop it up, unless you change the amount of substance. If you don't change the amount of substance, it will be constant. So you can see over here, your mass is the same, 60 kg, but your weights are going to be different. Okay? And before you ask, you don't need to memorize the 10 and the 1.7. The question will give it to you. The only one that you need to remember back until then will probably be Earth is always 10. Okay? That's all you need to know. So you just need to compare left-hand side, right-hand side, left-hand side, right-hand side. Just remember about 2 of them at least. But most of them, if you think about it, are things that we just now briefly mentioned. Beam balance, spring balance. Newtons, kilograms. Definition, gravitational force. Okay, that's all you need to know. The location one, I would say try not to use it. It's a bit more confusing itself. As long as you understand what is going on, then you're okay. Right, now last but not least, you have your density over here. Now, density, if you notice, is mass per unit volume. So, how do I write the formula? Now, you don't need to write this. You can write density instead. Okay, so D is M over V. So, don't write this. Use D. Okay. And if you notice, we'll be using SI unit, so it'll be kg and meter cube. Okay. So, but, we tend to use gram per cm cube often. Okay, so let's do it at the top. 1 gram per cm cube. If you all remember our unit conversion chapter, 1 grams is 1 cm cube, because the per something is just over. Every time you have unit something, is 1 unit of that volume. Okay, so what does that mean? I want it in kg, because SI, right, gram kg, I don't have the prefix, don't have divide, db, right? Positive 3 over 1 cm cube. 1 cm cube, I need to times 10 to the power minus 2, and because I have a cube, I will cube the outside. So we press this in your calculator. This is actually 1000 kg per meter cube. So they are not the same. Okay, they are not the same. Yeah, not same. Okay, don't make that mistake. Now, when we talk about density itself, if you have a bronze alloy, this is our mixture, right? Remember, our mixtures are usually stronger and tends to be a bit harder than your pure metals itself. So copper and tin are your pure metals. We'll make bronze, which is an alloy. So the thing is density, right? So your new density will just be your total mass over total volume. Okay, so basically this is, you can think of it as this is your brand new density, right? So to find total mass and total volume, same thing, like I said, if we have a formula, we don't rush straight into this. First, we find the individual components first. Ask yourself, what's your total volume? This one is easier to find. So first thing, I need the volume of copper and the volume of tin. So bracket 10.0, 15.0, and 5.0. Now, why do I use cm? Because the density they gave us is in cm cube. So because that, we take note of that. Next one, we have 8.0, 5.0, 3.0. As your calculator, make sure you put your brackets just in case. This side, you get 750. The other side, you get 120. So in total, I have 870 cm cube. Now, first, we want to find your mass, correct? So the thing is, density is mass over volume. Every time you see a word density here, straight away you write that. So now the thing is, we want to find your mass. So we'll move the volume on the other side. So to find the mass of your copper and the mass of your tin, this is what we need to do. Mass of copper. Density. Density of copper is 9.0. What's the volume of copper? We use 750. We get 6750. And this, it will be in grams because it's gram per cm cube. So we minus away the grams and we will get the cm. When we minus away the cm cube, we get the gram. So next one is tin. Tin itself is 7.3 and it has a volume of 120. Get 876 grams. So your total mass is going to be 6750 plus 875. 7626 grams. Okay, so last but not least, we want to find your new density. So we'll use your total mass, 7626, over your total volume, 870. You end up with 8.7. You have a very, very large number, 66512, blah, 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 so on, right? So what we want to do is this number is too big, we're going to round it to 3SF. So same thing, you look at your first 3 digits, then we'll look at this one. So this one is 5 or more, so because that we will round it up. So this will be grams per cm cube. Don't forget bracket 3SF because we rounded it up. So you can see over here, this will be our final answer, and therefore this is the final answer for this. So now the question is, we learned about density. We know that density is mass per unit volume. So what's the point of having density? Do you remember when we go all the way back to your first question, first topic? We learned about your physical properties, and we learned about one of them is density. Density is mass over volume, right? So this is actually to help us identify if something floats or sinks inside the liquid itself. So condition number 1, if you are less dense, you will float. If you are more dense, you will sink. Now, there's a very unlikely scenario where density is exactly the same. So this is remain suspended anywhere. So I'm gonna color code it. If you are less dense, you float. If you are more dense, you will sink. And if you are very unlikely, you will be suspended somewhere, not floating, not sinking, you'll be somewhere in the middle. So the thing is, water is 1. So if your number is less than 1, you will float. If your number is more than 1, you will sink. If you are the same number, you will be suspended somewhere in the middle. Now, take note over here, when you actually draw your, give me a second, when you actually draw your floating object over here, you will notice that it is not sitting on top of the liquid. It will be somewhere partially submerged. Okay, so because of that, to take note, you should have them partially submerged over here. Okay, now, if you write your formula, density is mass over volume, right? Now, mass does not affect your floating or sinking. Does not. Why? Because it is your density that determines it. Same material, same density. So regardless whether I use an iron sword, iron cube, iron ball, iron rod, any kind of iron object, they all have the same density of iron. So same thing, if my object, if I'm using the cork over here, the one for the wine bottles, if I'm using this, regardless of whether I have one gigantic size one or a very, very small one, both of them will float because they are made of the same material, and therefore they will always be less dense than the water, so they will float. Okay, they'll always have the same density. All right. Now, immersible liquid itself, this one is basically cannot mix. So liquids that cannot mix, they'll form distinct layers where on top you are less dense. Because remember, low density, you float, right? So if you are less dense than the other liquid, you actually float on top of the second liquid. So if you see here, you have vegetable oil, water, and mercury. Mercury is very, very, very dense, so it's actually all the way at the bottom. So the thing is, sometimes question will actually ask you to draw. So if you want to draw itself, we will have your beaker. The first thing we draw, number 1, is the liquids. So let's say we have the 3 layers on the other side. We'll draw the heaviest one, second one, then the lightest one. Okay, so basically you have these liquids, you want to label what they are. This is your oil, this is your water, this is your mercury. And do take note, we use pencil to draw, and then second step, you add in the solids one by one. Then third step is to label all of them. Okay, So the thing is, if you have a floating object that is less dense than oil, and we'll place it on top of oil. Take note, you're floating on top. Then if your object is less denser than oil but less dense than water, it will form this way. Okay, but if you are denser than water, you will be over here. And last but not least, if you are denser than mercury itself, then you will form all the way at the bottom of your liquids. So you can see something like this, then you label each and every one of them, and you notice which is which. Iron, which is 7.87, is less than density of mercury, but is more than water. So because that, you will sink in water, but float in mercury. So that's why you have all of your different shapes and sizes that you see over here. Okay, so we always draw liquids first, use a pencil to draw, and then you add in your solids. Okay, so this is how you are supposed to draw so that we know which floats and which sinks accordingly. Okay, so that's all for your physical properties chapter itself. If you have any questions, feel free to drop the center message. If not, that will be it for